Like in many other serial communication protocols, in CAN bus we transmit information from one place to another using a series of digital pulses. Ones and zeros, highs and lows, kind of like square waves. What's kind of different to other kinds of communication protocols though is that in CAN we broadcast this information simultaneously, inversely and independently on two separate conductors called CAN high and CAN low. In CAN, both of these conductors maintain a resting voltage of about 2.5 volts. That's the default state of the bus. And participants on the network can communicate information by disturbing the bus from this state with a pulse. Now, this pulse will take different forms on the two different lines. On the CAN high line, a pulse represents a 1 volt rise from the resting voltage up to 3.5 volts. And on the CAN low line, a pulse represents a 1 volt drop from the resting voltage down to about 1.5 volts. In other words, on the CAN high line, a pulse is represented as a high, and on the CAN low line, a pulse is represented as a low. Part of the magic of CAN is that participants don't identify the bus state from either one of these conductors, but from both of them together. Using a process called differential signaling, which is basically just subtraction, we take the bus state to be the difference in voltage between these two lines. Interpreting the bus state from this delta voltage is preferable to looking at either of the two lines independently for a range of different reasons. The first being that this differential signaling basically eliminates noise. We tend to run CAN conductors throughout a network in what's called a twisted pair, and part of the reason we do this is to ensure that any electrical noise that's induced on, say, the CAN high line is also induced on the CAN low line. And then when you subtract one from the other, this noise is basically eliminated. The other reason why looking at the voltage delta between CAN high and CAN low is preferable to looking at either independently is that it gives us a really nice, strong signal to noise ratio. When a pulse occurs and CAN high goes high and CAN low goes low, we see a 2 volt difference between these two. And when a pulse is let off and both return to the resting voltage, we see a 0 volt difference between the two. Now, importantly and somewhat confusingly, the logical bit stream, the bus state, is interpreted from this voltage difference in a pretty counterintuitive way. In CAN, we interpret a logical 0 when the difference between CAN high and CAN low is 2 volts, when both are being pulsed. And we interpret a logical 1 when the difference between these is 0 volts, when they let off the pulse, when the bus returns to its resting voltage. To help avoid confusion between the state of the bus and the state of the individual conductors, we refer to a logic 0 as a dominant bit, the state that's taken when there is a large difference between CAN high and low, when the bus is being pulsed. And we refer to a logic 1 as a recessive bit, the state that's taken when the bus returns to its resting voltage and when the difference between CAN high and CAN low is 0 volts. These names, dominant and recessive, are intentionally used to avoid confusion between the relative high and low state of the bus and the high and low states of the CAN high and CAN low conductors. And for reasons that will become apparent when we start to talk about arbitration, when we get to the data link layer of the CAN standard. It's probably important to note that in general, only one participant is speaking at a time in CAN, disturbing the bus, but there are a few specific instances where more than one participant might try to speak at the same time. When a participant tries to influence the bus, it's said to be asserting a state. When it pulses the bus away from its resting voltage, it's said to be asserting a dominant state. And when it lets the bus fall back to its resting voltage, it's said to be asserting a recessive state. As the name kind of suggests, if one node were trying to assert a dominant state and the other were trying to assert a recessive state, the dominant assertions dominate. We'll talk a little bit more about this when we get to message arbitration.